but there's not much sense in doing.
So we are going to cover the very last type of conic. There are only 4. There are no more than 4. So we're going to talk about the hyperbola, which is the last conic of the group of conic sections. And the final conic is the one that is found by using 2 cones, the actual double napped cone. So if I had a cone, another one sitting on top of this, a hyperbola would slice through both cones, going down vertically on the side. So my plane slices through both cones, creating 2 parabolas, which together they're called hyperbolas. And again, they're not truly parabolas, but that's kind of the shape that they would have. So another one going up, plane slicing down the side, plane slicing down the side to create the hyperbola. So we are going to talk about the hyperbola today. Of course, we will look at the graphs of the hyperbola. We'll talk about the standard form of the hyperbola. And then if you remember from chapter 2 this year or chapter 8 last year, rational equations. So the equation y equals a over x, y equals 1 over x, 2 over x, 7 over x. The graph of those are also called hyperbolas, and they have 2 pieces to them. And there's also asymptotes in the graphs, creating the width of the 2 pieces. So these functions will have asymptotes. So that kind of is part of the graph of a hyperbola. It's bounded by the asymptotes. So they help create how wide or how narrow our parabola would be. So we'll look at that as well. Homework tonight, just like all of the other conics, the first group of problems are matching. So 7 through 10, again, I ask that you show some type of work and not just have a letter written down. And then 13 to 17 odd, those are the problems where you will not need to complete the square. They're supposed to be the easy problems that are pretty much in standard form, just getting you to find the vertices, find the foci, and now find the asymptotes. 25 to 29, those 3 problems, you'll have to complete the square to get it in standard form and then find the information. So tomorrow's homework then will be the flip, just like all of the other days, where we'll be given information about the graph, and we'll try and use that information to create our standard form of the equation. So we're gonna look at a hyperbola today. If you want to take out your notes and notability for section 9.3, test coming up next Tuesday on the 4 conics. And then, as I said, we start the last chapter on Wednesday next week. And that last chapter, chapter 11, is on limits. Today marks, I believe, the 20-day mark. 20 days of school, counting today. It just seems insane crazy. Parts of it seem like it's been a long year, but I feel like since everyone's been back, it's just flown by. I mean, March and April were just like a blur. May starts on what, Saturday? May 1st is on Saturday? Yeah, because April only has 30 days. So, all right. So a hyperbola, the definition of a conic starts out with the set of all points. It has to meet a certain geometrical condition. And the condition that a hyperbola is meeting is the difference of whose distances from 2 distinct points is called the foci is constant. So a hyperbola and an ellipse are different because an ellipse is the sum of whose distances from 2 distinct points is constant. And a hyperbola is the difference of the distance from 2 distinct points is constant. So ellipse is sum, hyperbola is difference. And I grabbed a picture out of the book. We are going to make, of course, our own graph, but just so that you can see, Here is a picture of a hyperbola on the left side of the screen. And we still have a focus. Again, kind of think of it like two parabolas going in the opposite direction. But if you have a point anywhere on that curve, the distance to get from that point to the focus and that point to the second focus, if you subtract that distance, it's going to be constant no matter where you are on the curve. So that's what makes it a hyperbola instead of an ellipse. An ellipse would be adding that distance and it would be constant every time. So we are going to look at graphing this here and trying to kind of label all of that information. And then we'll talk about the standard form. But going through the graph will be a little quicker because you know there are two vertices, you know there are two foci values, and that information will be found the same way. So we'll start with our graphs. We're going to locate the information underneath. And which one do you know? Do we usually start with the horizontal or vertical? I don't remember. Guess we'll go with horizontal first. So a parabola has the axis of symmetry, and they just call it the axis. An ellipse has a major axis because the major axis is the longest one. It would be really nice if it worked the same way with a hyperbola, but of course it doesn't. So a hyperbola has what we call a transverse axis, and that's the segment connecting the vertices. So the major axis is also the segment connecting the vertices, but it's the longest one. In a hyperbola, it is just called the transverse axis, and again, it's still that segment connecting the vertices. So a horizontal transverse axis. So the transverse axis does connect your two vertices together. So this is our transverse axis. And it's going horizontal. On the ends of the transverse axis would be our vertices. So we have one vertex and we have the other vertex. Each vertice creates a branch. So that's what the term is actually called. They look parabolic, but they are actually called branches. So we would have a branch going through the vertex on the right and a branch going through the vertex on the left. And they should be the same size. Mine were not. So let's try again here. Try and make them look a little more the same. The center is in the middle of the two vertices, just like it is for an ellipse. And the center is still H and K. So the center is still the center of an ellipse, of a hyperbola, of the circle. It's in the middle. The foci, it says, is C units from the center. The foci is always inside the conic. So it's inside the ellipse, it's inside the parabola, it's inside both of these branches. And it's saying that the distance from the foci to the center, or from one focus to the center, is still C. So that information doesn't change. So the distance from the center to a focus is the distance of C. Same thing with the vertices. The distance from the center to one vertex is still A. So A is the distance from the center to a vertex. C is the distance from the center to one focus. So those two parts are the same for an ellipse and a hyperbola. So we have a transverse axis, which is the line segment connecting the vertices. If that is horizontal, everything lies on the same horizontal line. The vertices and the foci are on the same horizontal line. The last axis is called the conjugate axis. The conjugate axis is like the minor axis. It's the axis that goes in the other direction. So the conjugate axis is going to help us determine how wide or narrow your branches are. And that axis, in this case, is going to go vertically. And we will talk about more about that once we start looking at the asymptotes of this graph. The conjugate axis is B. So to get to the end of the conjugate axis, that distance is our distance of B. And again, those endpoints, they don't really have a special name, but it still is the width of the graph, or in this case, the height of the graph, but it helps control the width of our branches. So I'm going to shrink my picture a little bit because I want to write down underneath. Just as a little reminder, we have the center, it's still H and K. We have two vertices, and when it's horizontal, the H value is the one that's changing by adding or subtracting A. And then we still have those two foci, and again, the H adding or subtracting C. So that's the same exact information for a hyperbola and an ellipse. You find the vertices, you find the foci in the same manner. So we're going to quickly flip this around and have a vertical graph. So we'll draw a quick vertical graph and we'll talk about the equation. And then, as I said, we're going to look at one other part, and it's those asymptotes. So a vertical transverse axis. So essentially, it's taking your horizontal graph and flipping it so that it's going up and down instead of left and right. So the transverse axis is now vertically going up and down, connecting your vertices. And it just connects the vertices, so it doesn't stretch all the way to the focus. And that's the same thing with your major axis. Your major axis connects the vertices together. The transverse axis connects the vertices. So we have these two branches. Now going up and down that are connected at the vertex. So A is the distance from the center to the vertex. And C, is the distance from the center to the focus. Notice that focus, that distance from the center to the focus is now going to be bigger than the distance from the center to the vertex. So, and that distance has to be larger because the focus is always inside the conus. So that distance of C is now a larger distance than it would be from the center to a vertex. So C should be bigger than A. Questions? So on the side, just kind of summarizing here, the center is HK. The vertices, once it's vertical, your K value, adding or subtracting A. Yeah. Yeah, I just didn't draw it. Thanks for catching me there. Yeah. So just because it's vertical doesn't mean it doesn't have a conjugate axis. Yes. And that distance is going to be B. So this time transverse axis is vertical, conjugate axis is the horizontal distance. Transverse axis is the distance from A to the vertex, or the center to the vertex, which is the distance of A. And then the conjugate axis is the distance of B. So now we're graphing branches. Two branches make a hyperbola. So a hyperbola are two congruent branches. They're going to be the same on either side. They just flip and go opposite directions. So the standard form of the equation, this is the last pair that we have to look at. So we'll keep it the same so that horizontal is on the left. And vertical is on the right. So what do you think is going to happen with the equation? Thinking about the other equations, what would the equation probably have in it? What do you think it would look like? What do all the other equations contain? Peter? An x squared. What else do they contain? What are their letters? A y and Darby? H and K. All of them have had an x, a y, an h, and a k. This is going to have both x and y squared, just like the ellipse, x minus h squared, y minus k squared, equals 1. I left out the symbol in between though. So an ellipse is the sum of the distances, and a hyperbola is the difference of the distances. So a hyperbola has a subtraction sign in the middle. In the denominator, a squared, b squared. A squared is always going to be first. The positive term gives you the direction. So if x is positive, then it's a horizontal function. A could be bigger than B, but it doesn't have to be bigger than B. It's not called a major axis because it's not necessarily the biggest axis. So the term that's positive is the direction that it goes. So if x squared is in the front and it's positive, then it's a horizontal graph. But again, a squared is always first. A does not need to be bigger than B. It's always first. So for the vertical graph, the standard equation would be y minus k squared, x minus h squared, And again, there's a minus in between. So now the y is in front, but again, a squared is still first, b squared is second. So the denominators aren't switching this time. It's the numerators that are now switching. So what variable is in the front? Which variable is positive? A is always first, B is always second. Questions? So we're going to skip the example underneath, and we're going to look at one more piece to these. Each conic has kind of had one extra part than the previous conic that we've discussed. And as I said, this conic has branches, and those branches are actually kind of created by asymptotes. So it says, as you move out on the branches of the hyperbola, the branches approach asymptotes that are kind of creating the width of the branch or how narrow the branch would be. So the asymptotes, I'm going to draw two more quick sketches, depend on, is it a horizontal or is it a vertical graph? So we'll look at horizontal one more time. Versus vertical. And I'm going to draw a little quick basic graph. So we have our center. We have the vertex. And we know that they are connected by what's called a transverse axis. The distance from the center to the vertex, we said, was A. There is also a conjugate axis, and that goes in the other direction. It goes up and down. And that distance is B. The way the asymptotes are created, God bless you, is by drawing a box and connecting your vertices and your conjugate axis together. So essentially we're connecting the transverse and the conjugate axis together. So we're going to draw a little box here going the entire width, top and bottom, and then the height. So I went vertically through the vertex on each side, horizontally through that conjugate axis, the endpoints of the conjugate axis. The asymptotes cross through the center of your graph and the corner of the box. So the asymptotes are going to go through the center and the corner of our box. And that is how the width of the parabola or the branches are created. So the parabola or the branches skim along the asymptotes. Now, of course, the asymptotes actually have an equation. And that equation is found by taking the k value from the center because that's where your equation for the line of the asymptote is going to start. Now, an asymptote's a line, y equals mx plus b. It increases, it decreases. So it's going to start or have a y-intercept of the y value of the center. And then, because there are two of them, you're either adding or subtracting the slope of the line. Now, slope is what over what? Two basic words to describe slope. Rise over run. So if I look at my graph here, the slope of this line, the rise is B, the run is A, and that's how I get to the corner of my box. So the slope of this asymptote is B over A, because the rise is B and the run is A. It's a positive or negative because one line is positive and the other one is negative. And then in parentheses, it's x minus h. So the center of your graph creates the equation of your asymptote because it's going to have a y-intercept of the y value of the center, and it's going to shift right or left depending on the x value of the center. The slope is the vertical distance up A, rise, over, I'm sorry, up B, and then over A to run. Questions on that equation for the asymptote? So if you take that graph, quickly do a little rotation of it. And one final graph here, and then of course we'll look at an example. But again, we have a vertex, we have the center, we have another vertex. And then you have that transverse axis connecting the two vertices. That distance is A. The conjugate axis goes the other way. And that distance is B. So you make yourself a little box going through the vertices, through the endpoints of the conjugate axis. And then that little box creates your asymptotes. So through the center and the corner, center, corner. And this time your parabola is going up and down, or your branches are going up and down. So the equation of the asymptote is still k plus or minus. But Kaden, what is the slope of the line now? What's rise over run if it's a vertical graph? Yeah, it's A over B. Because now I'm rising the distance of A to get to my vertex, and I'm running the distance of B to get the width of the graph. So K and H aren't changing. The only thing that's changing is the slope. And that's because the location of the vertex is now vertically. So that distance from the center to the vertex is the distance of A. So that's a lot. Again, that first day, a lot of information about these graphs. The conic. Questions? So, Darby. This part here? Oh, because thinking about your line y equals mx plus b, the k is the y-intercept. So the y-intercept would be the y value of your center, and that's not going to change because it's always just the y-intercept. So this x minus h, like when you're talking about the equation of slope, x is always contained with the h, so mx plus b. It's still kind of in that form. Other questions? So what I'd like you to do is to see if you can look at the equation that's given underneath. And I want you to take this equation and transform it into standard form. So 4x squared minus 3y squared plus 8x plus 16 equals 0. So complete the square, get it in standard form. So there are definitely similarities with each conic. We have to take something into standard form by completing the square every time. Besides the circle, all the other ones do have vertices, or at least a vertex, and foci, or at least one focus. The y squared is by itself, so you don't need to complete the square with the y term, because it's just y squared. You do need to take the 4 out of the x term. And then Hannah, what number did you plug in with x? A 4. And on the other side,
Would you just put in 0?
yeah, here, you would just plug in 0 there, yeah. So you would just plug in a 0 on the other side, not a, you said a 4, I think you meant.
Yeah.
I know what you meant. You meant plus 4 over here, yeah. Okay. So this would be 4 and then x plus 1. And then you're just gonna keep minus 3y squared. Again, you would technically have a 0 there. And then it's equal to negative 12. So what would you have to do to get it into standard form? We completed the square. What's next? Peter? Yeah, and it's negative. There's supposed to be a positive 1 for it to be standard form. So you're dividing both sides by negative 12. Peter, what happens when you divide both sides by negative 12? Nice. So the y squared is positive. Move that to the front. You're subtracting and dividing by a negative 12. So that becomes the positive term. The x is now negative because it's 4 over negative 12. So that would go second. And that's over 3. And then it's equal to 1. Questions on that information? Parker.
Why did it go from x plus 1 to x minus 1?
Oh, I don't know. Because I missed. Thanks, good catch.
So the standard form of the equation, you subtract in the middle, right?
Mhm.
So did you not do that in the first step? Because I wrote it as like minus negative 3y squared.
Oh, you could write that first. I mean, you could, but it ends up flip-flopping because there was a negative on the other side. Yeah. So, I mean, I would keep it the same and rearrange it at the very end. Yeah. But like what you did wasn't wrong. Yep. Other questions? So we flipped it here. You ended up doing that in the first step. So is this graph a horizontal or a vertical graph? Grant, what do you think? Horizontal or vertical? Yeah, why? Exactly. So y squared is first. It's the positive term. This is a vertical graph. Now, a squared is always first. B squared is always second. So a is 2 and b is the square root of 3. And then I just realized I didn't define c on the other side. C squared is now a squared plus b squared. And it's adding them because that distance now needs to be larger than a, because it has to be further out to be inside those branches. So c squared is taking 4 and 3 and adding them together. So c is the square root of 7. I apologize for forgetting that on the front of the page. Sorry. A is always first, B is always second. All right, so Grant said vertical. To find the vertices, you're adding or subtracting A with the Y value. To find the foci, you're adding or subtracting C from the Y value because it's vertical. Be careful with the center. -1, 0. That would be our center. H is still with X. K is still with Y. So -1, 0. So that means our vertices are at -1. And then K is 0. You're adding or subtracting 2. So -1, +2, -1, -2. The foci, again, -1, adding or subtracting C. Well, 0 plus the square root of 7 and 0 minus the square root of 7. So make yourself a little graph, XY axis. We're going to plot the points and then we'll make those asymptotes for our branches. So the first point, the center is at -1, 0 on the x-axis. You're going vertically up 2, down 2. Those vertices are -1, 2, and -1, -2. Your foci should be further away from the center because they need to be inside the branch. And that distance is the square root of 7, a little less than 3. So they should be further from the center. And then the last part is the B. That gets us the other direction, the width, so that we know how wide the branches are. And the square root of 3 is a little less than 2. So from the center, a little less than 2 in both directions. So we're going to make a box. That box goes through the vertex, through your conjugate axis. Make sure it doesn't go through those foci values. The foci values should be hanging out by themselves. And then your asymptotes go through the corner of the box, through the center, both directions. Start at the vertex and then make your branch. That vertex should be on the edge of the box. So the very last part, it says to write the equations of the asymptotes. So K plus or minus, it's vertical, A over B, and then X minus H. K is 0. A is 2, B is the square root of 3, and then it's going to be X plus 1. And you can keep it in unrationalized form. so that the slope corresponds directly with our graph. So a lot of information. Again, you've got a few problems to work on. The first one will go a little slower, and then you'll kind of pick up pace as you work through the problems. Have a fantastic day. See you tomorrow, Parker.
Square root 7 under the 2?
Yes, square root. Oh, under the 2, it's a 3. It should be your B value. So square root 3, square root 3. Thanks, you too. Thanks, you too.